So let's talk about electric field. Electric field is a really interesting thing. If we were to take a small positive test charge at some point near a negative charge Q, what will be the electromagnetic force at that point? So if we have here our test charge, this is a negative charge, so I'll put a little minus sign there to kind of indicate that. That's our negative charge. What if I put my positive charge, here's my little plus guy, plus right there. If I put my positive charge there, what is the electromagnetic force? So now remember, uh, the force is going to be attractive because they are opposite sign. So the force is going to point towards the negative charge. What if I put one down here? Another little positive charge. Then that guy's going to want to point upwards towards the negative. So I can do this a few times and I can see where the charge wants to go. It's always towards. Now, why are these arrows in the center so much bigger? Well, it's because the closer they are together, the stronger the force. Remember, it's divided by r squared. The value of the force, F equals KQ1 Q2 over r squared. So because r is on the bottom, the smaller the r value, the larger the force. It's just like gravity. When two objects are closer together, they feel a stronger pull. And so just like with gravity, we have the same thing with charge, that the closer the objects are to each other, the much stronger the force actually gets. And the farther away they are, the weaker it gets. So that's why these charges out here feel such a weak force as compared to these charges towards the middle, which feel a much stronger force. So what if we wanted to look at this in general? If I wanted to kind of draw something to show what would a charge want to do near this negative charge from any place? We can do that. And this is what it would look like. This is the electric field of a big fat negative charge. Here's our negative. So you can see that the electric field points towards the center of that charge. What that basically means is if we take any positive charge and place it anywhere around this negative charge, if I put it here, for instance, say I placed a positive charge there, then the arrows that are nearby tell me, hey, this is the direction of the force that that charge is going to feel. And it's how big it is too. So that's why you can see the arrows that are towards the middle are larger, and the arrows that are farther away, if I have a charge that's a little farther away, it's a smaller arrow, meaning a smaller force. So you can draw electric field lines that show generally what the force would be on a small test charge that's placed anywhere in that region. So taking a look at the electric field, let's find a mathematical way to represent the field. We start with Coulomb's law, which is the force equals Coulomb's constant times Q1, Q2 over r squared, as we've been doing. The electric field is defined as the force per unit charge. So it's kind of like saying F equals ma for a but for electricity. So F equals ma, except for electricity, it's kind of like saying F equals QE. So I didn't draw that very well. QE, that still doesn't look great, but whatever. So charge is kind of like mass, and here the electric field is kind of like acceleration. So the electric field gets multiplied by the charge in order to equal the electric force. Now you can isolate the electric field by just dividing both sides by charge, and so if you take the electric force on a charge and divide it by that object's value of its charge, then you get what the electric field is at that spot. So if we replace then the force with Coulomb's law, if we just take Coulomb's law right here and substitute that value, then we get, you can see here, this is basically Coulomb's law on the top there. Oh, including the K, sorry. Then we end up getting these Q's cancel, and we get something that just looks like this, KQ over R squared. So the electric field is exactly the same formula as the electric force, only missing one charge. So it's as if you're just looking at the field of a single charge that's far away and you don't have another charge to measure the force against. You're just measuring how strong the field would pull on a charge if it were there. Okay, so the electric field is something that we call a vector field. It's basically a representation of the vectors that show where the electric field is pointing at all places. So it just kind of shows you where you can pick any point and you can immediately determine where and how large the field is going to be pointing at any spot due to a particular charge. So it's called a vector field because it's a field of vectors. It just, if you remember the picture from earlier, it's kind of like looking around and seeing just a bunch of vectors everywhere that are pointing in the direction that you need. It's not that bad. Try not to be too worried. I know that you guys freaked out a little bit before with vectors, so try not to worry too much. All non-contact forces have a field associated with them. So just like we're talking about here with an electric field, gravity itself also actually has what we call a gravitational field. So you could, if you wanted to, define a gravitational field by taking away one of the masses from the formula. Now, we didn't actually do this, but if you go on in physics, such as if you do college level physics, you'll actually talk about something called a gravitational field, and you can actually measure it and calculate it, just like we're doing here with the electric field. So electric field vectors always point in the direction that a positive charge would move if placed in the field. So that's why earlier we used the example of a positive test charge that we put near the negative charge in order to see where it would want to go. So if you look here, we have in figure 1624, we have the electric field at a given point in space. So the force that this charge would feel at that point, if we have a little test charge plus Q, the force is right there in the same direction as the electric field. Of course, the magnitude of the force changes depending on the value of the charge. Now you can see if we have a negative charge, that the force is actually going to want to go in the opposite direction. That's because the minus sign changes the direction of the vector, flips it around. Makes sense.